Okay, shall we get started?
Yeah, that works for me.
All right. Hi, everybody. My name is Dieter Fox, and I'd like to welcome you to the UW Robotics Colloquium. This is the last colloquium of the quarter, and it's my really great pleasure to introduce Maria Bauza Viallonga. She is today's speaker. I've known Maria now for quite a while, right? Like since you started your PhD, and I've been an admirer of the work because it has this really nice connection between machine learning, different tools from machine learning, Gaussian processes, nowadays also, of course, more and more deep learning, and real practical relevance. So a lot of the work has, I think, a really strong connection to industrial applications, especially for robot manipulation. So Maria is doing, or currently also finishing up her PhD at MIT, working with Alberto Rodriguez. I think the high-level theme is mostly about like what happens when robots make physical contacts with objects in a scene, analyzing that and predicting how objects move and what governs the motion of these objects. And I think in the early phase, it was a lot about, let's say, planar kind of motions, right? Where objects are on a plane, and it's mostly about this 2D motion along with rotation. But more recently, Maria moved on also to much more open-ended connections between the robot and these objects, using the gel slim sensor in order to get much richer sensor data to investigate kind of the contact points and the physical interaction between the robot and these objects. And that, of course, also allows much more capable models to be learned in order to predict 3D poses and things like that of objects. And I think that's, of course, a really exciting development. And today, Maria is going to talk us about her most recent work on picking and placing of novel objects, but doing so with high precision. Thank you very much, Maria.
Thanks a lot for the introduction, Dieter. It's a pleasure to be here. So as Dieter already said, my name is Maria Bauza, and I'm a PhD student at MIT. And today I want to talk about how do we achieve robots that can solve many tasks without compromising on their precision. Usually, when we think about robots, we think about a robot that can interact with us, that can reason about the task that we command it to do. And to me, what is also very important is that this robot needs to interact with the world. It needs to be able to manipulate. And if we think about how humans manipulate their environments, we are very dexterous. So here's an example. We have these persons that are actually interacting with all these small pieces. They are all different, but they can just place them and assemble them with high precision. So how do we even get robots to get to this level of accuracy when the pieces and all the environment keep changing? So how do we get this dexterity in manipulation? This is one of the questions that my research looks at. But if you look at today's robots, we will think about an industry and automation. And what's going to happen is that robots can be very powerful, very precise. They can even solve tasks that we cannot do, like welding something very precisely. But this is only restricted to the setting of one robot, one task. So we don't have robots that can really solve a lot of things. And this is true even today. If you look at the survey that was conducted just very recently in 2020 of the state of industrial robotics, what they found is the following. If the industries need to make a small change into a line, this causes a lot of problems. And this is because those lines are actually with robots are set up to do something very precise, but also very specific. And if you need to make a change, this creates the inability sometimes to even reuse those robots, to the point that some companies have told actually it's more economical to just remove all the robots and get new ones. So to me, this really shows this problem of one robot, one task. Instead, if now we look at research, there has been some progress towards how do we generalize? How do we get robots to do something that is more general, that does something more than just one particular task? And in our group, we have actually looked at things like, if we have novel objects, how do we grasp and drop them, or how we just pick them and throw them into a box? And this can be done for novel objects, but it comes with a problem if you look at it closely, which is that the methods that we are using don't really require a lot of precision. And this is because the task itself doesn't require a lot of precision. In this case, we are just dropping the objects, and that's perfectly fine because all we wanted to do is just throw them and put them into a box. So in these cases, we are definitely not aiming for models that we could say can lead to precise tasks. And this is true for other cases, like in these two ones that I'm showing here. One of them is just, can we flip shoes? And this work is really nice because it can generalize across different categories of objects. So it has, you can do that for many different shoes, for instance. And in the one on the bottom, you are placing some objects, but actually if you look at it carefully, we are just dropping them. So I would argue that these works also suffer from the fact that we don't have, even on the tasks themselves, don't ask for a lot of precision. And this is something that I really want to address. I want to see, can we do robots that can solve tasks with precision while being general? So the concept that I want to talk about is this idea of precise generalization. How do we get a robot to solve multiple tasks without compromising on reliability, accuracy, precision? And this to me moves us into the paradigm of one robot, many jobs. One example that I like when I think about that is, can we get a robot that is capable to assemble most of the IKEA furniture, instead of just having to do maybe one object for each of the furnitures that we want to assemble from IKEA? So that would be a really nice goal. It's challenging, but again, it would move us much more closer to this idea of precise generalization where a single robot can do all of these tasks. And to me, we want to do that with out of the box. So that means that the robot, maybe you give it some object models, you give it some instructions, maybe something like this, and then it's capable to just go ahead and assemble the new piece of furniture that we are giving to it. But to me, that comes with some requirements. And those requirements are a bit different than what maybe we are usually thinking about in robotics. The first one is that I think we need general perception models and skills. That means that we don't want to relearn for each of the tasks how to do perception, how to localize objects, how to understand how many objects are in the scene. The second one is the skills. Screwing an object, probably you don't need to learn how to screw every different bolt every time. There is some fundamentals that you can probably extract that then you can reuse across different tasks. In this case, it would be across different assemblies. Another one that I think is very important is probabilities. Because we are thinking about being precise. When you want to be precise, you need to fight against uncertainty. You need to be able to handle uncertainty so that you can make sure that you achieve your goal with precision. So that means that you have to reason about probabilities. So this is going to become more and more important the more precise we want our task to be. And then finally, we also need to think about task awareness. If you want to be able to solve this task, like assembling an IKEA furniture, the actions that you take can be useful, not just for the precise thing that you're doing, let's say screwing, but I need to take into account all the rest of the actions that you will need to take. So for instance, if you move in a way that occludes the object, that might be hard for you to go into the next step. If now instead what you're doing is that you're just grasping a hammer by the wrong end, then it's going to be hard for you to exert the right amount of forces. So task awareness is also going to be very important in order to achieve this idea of precise generalization. In today's talk, I want to talk about something that it's not assembling IKEA furniture, but it's also very important. It is definitely a component of assembly, which is pick and placing. Pick and placing is actually a big challenge in industry because pick and placing means you might found an unstructured environment, like in this case, you have many objects just in front of the robot, and now you want to go and place them very precisely into a known configuration. So now you're going from something that is unstructured to something that is structured. And if industry was able to do that, that would be a great progress because now once you have something that you really know where all the objects are, where are their placements, then the rest of the task becomes really simplified. And this is something that even industry is still struggling, especially when we would say we want to do this for novel objects, for objects that we have never seen before. If you give it to me, can you do reliably this precise pick and placing? For today's talk, I want to just show you how it's going to look like. So this is me, and these are the objects and the placements that we want to do. So as you can see, here I'm placing the object into this holder. And depending on how I grasp, as you can see, I may need to do some actions to allow me to place these objects. So in this case, I had to do a regrasp. And finally, you can see that the placements are tight. So actually in this object, there is only 0.5 and 0.5 tolerance. So these are tight placements. So we want the robot to solve that. And this is how it's going to look like. So I'm already just show you kind of the solution. So the robot is going to go, is going to pick this object, is going to do a regrasp if needed, and then it's going to go and place it into the desired location, a location that we just specify. And now the question is, how do we get the robot to do that for novel objects? So this is what I'm going to talk about today. So let's go a bit more in depth into what it means precise pick and placing. So the first thing is going to be, we need to pick the object. Once we have an object that is picked in our hands, then we will be able to localize it. So that means answering the question of what is the object with respect to the robot hands. Once we know that, then the goal is place it in these precise locations. But it's going to turn out that sometimes, as I was explaining, we won't be able to just go and place it. We might need to do what we call a regrasp. So change the object from one hand to another until it is in a configuration that is suitable for us to then just go and place the object. So let's look a bit more in depth of what this implies. The first thing that it implies is that the robot needs to be able to perform a stable grasp. A grasp that when we close the fingers, the object basically is going to remain inside the fingers, not as it happened in this video. So now let's say that we know how to do a stable grasp. The next thing is going to be, can we localize the object? So we are going to be able to tell where is the object posed, and that is going to require us to build some perception models. And these perception models, we are going to build them from two sensing modalities. One of them is going to be vision. There is a camera mounted into the scene. And then there is going to be also these fingers that are actually tactile sensors that are going to give us also tactile information. So now you can see here how it looks like. These are the images that come from the sensor. We will talk a bit more about this sensor, but just for you now to understand these blue images, each one of them comes from the fingers of the robot. So what's going to happen is that now when the robot closes the fingers, we are getting some contact on the object that then we can use with our perception models to predict the object pose. But now the key thing is to remember that tactile is local. We only see through tactile the places where we are making contact. And this means that we need to be careful about where we are making contact. If you make a zoom into this final configuration, there is actually perception failure because the true object pose, it's hard to see, but basically it's there where I plot it. And actually the perception model predicted this pose, which is clearly wrong. This is because actually the contacts that come from the tactile sensor were non-discriminative. They were not useful enough. I will argue that the way we can solve that is aiming at grasps that give us observability, that give us good information that then our perception models can use to understand what is the pose of the object. So basically, can we aim at grasp from the object that help perception, that I can take into account what is the task and give us useful contacts that give us information about what is the object. So if now we do that, we're going to be able to localize the object. So now we're going to be performing a grasp that is not just a stable, but is also giving us good contacts. I know those are hard to see, but those are actually useful contacts. And then finally, what we're going to have to do is to plan how to place the object. So here you can see that there was a planning that just happened. And now we're going to perform one grasp. But once we perform that grasp, it's not going to be sufficient. So we're going to have to do a second one. So now you can see how the robot is just passing the object from one hand to another until it reaches a configuration that is good enough for the robot to just go and place it. But it took us long to get here. It took us to regress. And actually, this is very dependent on where we make the initial contact. So again, what we are going to have to do is, can we aim at grasp on that object that minimize the number of regraspings that we have to do? And this is, again, something that is task awareness. So we want to minimize the number of regrasps by aiming at an initial peak that is good, that gives us a good initial configuration of the object that then is suitable for us going and placing the object. So these are, again, components that we are going to need to have into pick and placing. So now if we have everything, This is basically now we're aiming for a grass that is stable, that is observable, and that finally reduces the number of steps needed. Then if we do that, we're gonna get much better tactile imprints that are discriminative. And finally, we're gonna be able to plan for motions that are simpler. So in this case, with just one regrasp, we're capable to just go and place the object. So hopefully that gives you an overview of how this system of pick and placing needs to operate. And it needs to be able to do all this reasoning for this object, but actually for any new object that you give it. So how do we solve it? Our sensory inputs, as I already mentioned, are going to be depth and tactile images. Depth will look like this. Tactile images are those kind of blue images, but actually in practice, we're only going to use what we call contact images. Contact images are just a binary mask that is black if there is contact in this region of the sensor, white otherwise. So it's just something, a minimal representation of what it means, a tactile image. And now the first thing that we are going to get is this depth image. And from that one, we are going to do two things. The first one is sample possible grasp. So what are places where I could just put my fingers and grasp the object? And second, we are going to be able to do pose estimation from vision. Once we have that, we're going to be able to select which is the sample of the possible grasp that is best. So basically, you can imagine that we will say, actually, this grasp in here, where these red things are the fingers of the robot, seems to be the grasp that gives me better stability, observability, and dexterity. So minimal number of regrasp. And once we have this information, we're just going to go there and make contact. Once you make contact, now you get tactile information that you can use to actually update the pose estimation. And now that you know what is the pose of the object with respect to your sensor, so with respect to the robot, you can go ahead and compute what is the motion plan that allows me to go and place the object. So this is how it looks like. And in practice, it looks like this, where again, we're just doing the grasp sampling, identifying which grasps are good, selecting the best one, and also identifying from vision the object pose. Now we can just go, perform a grasp, and ideally this is going to be this discriminative contact that is going to allow us to update and get a better estimate of the object pose. And finally, again, we just go ahead and execute the plan. So we need to be able to learn all these components in a way that we can use them for different and novel objects. So basically, we need to learn this in a way that is general. And the way we do that is actually by using only simulated data. So we are not going to require any previous experience. All we are going to do is use simulation to learn all these components, so that by the time that we give the real system the object, it's already capable to perform pick and placing. So now let's go into simulation. In simulation, we are going to assume that we know the object model. And we're also going to assume that we know a way to simulate depth images and a way to simulate contact images. So this is going to be what we think tactile looks like, but just in the sense of where a contact is happening. If we know how to simulate those things, then we can learn each of the components of pick and placing. And for today's talk, I'm only going to talk about how we do pose estimation. So how do we use vision and tactile to estimate the pose of the object with respect to the robot? But I'm happy to go applying into any of the other components, but I'm just going to center myself into how do you do pose estimation in a way that is general, so that you learn it in simulation and then it just works for any real object that you want to estimate the pose. So again, we're going to do tactile localization. First, we're just going to look into how do you do tactile localization. And this is going to give us a general model. Given a new object, we're just going to be able to, in simulation, learn and then deploy it. We're also going to do it in a way that is probabilistic. So we are not just going to aim at giving one object pose, but actually distribution of possible object poses, which is going to allow us to then understand better where are the chances of us succeeding. And this is something that we are going to be exploiting. And we are going to be exploiting it in a task-aware manner. Basically, the concept that I was telling before of observability. If I make a contact in here, is that going to be useful for then tactile localization, give me a good estimate of the pose? So this is how we are going to leverage through these models this idea of observability. Can I identify if a contact is good or not? And if it is, can I plan a motion that aims at that contact? So let's go into it. Let's first talk about tactile localization. And the sensor that I'm going to be using is the one that Dieter mentioned. It's called Gel Slim. You have it here down, a paper where you can find all the details. But basically, in a nutshell, it looks something like this, where you have these sensors. I'm just going to show you one tactile image. And as we touch it with one of those objects, here you can see the object model. You can clearly see a very nice tactile imprint, which represents the deformation of the membrane of the sensor. And it's very high quality. It gives us a lot of information. And now the only question that we need to solve is, given this tactile image, what is the object pose of this object that generated that tactile image? But this problem is actually trickier than it seems, because tactile is local. And what that means is that different object poses can generate the same contact. If you look at this example, there are two poses. Actually, there is even more, but at least these two poses could have generated, right? If you imagine a contact in this middle region, just from this tactile image, it is not possible to say if it's this one or that one. So this is what we call a non-unique contact, a contact that could have been generated for different poses. And this is going to be very important because the existence of those non-unique contacts forces us to think about it probabilistically. There is this uncertainty. We need to now generate distributions of probability over estimates of the object pose. Otherwise, we just with a single estimate, we are not gonna be able to predict where is the object pose because tactile is local. So again, this is one of the objects, and now I'm just gonna show you just a different one so you can again see what is the problem that we're trying to solve. So given one of those tactile imprints, can we just generate a pose distribution of where we think the object can be? And because we're gonna solve this in simulation, we're gonna make an assumption, which is that we have access to the object model. So that means that in simulation, we are going to use this object model to train a general perception system that then can transfer into the real world. So let's look into that. Again, in simulation, we are going to have this object model. And now we can use it to generate what we call contact poses. A contact pose is no more than just a pose between the sensor and the object that is in contact without penetration. And here you can see them marked kind of in green. This is where the sensor is making contact with these objects. And now we can translate this into what we call the contact images. So this is just a binary image that is black if there is contact with the sensor. And this is what comes from simulation. But now in the real setting, we are going to have something that looks like this. This is our sensor. This object is making contact. Here you can see the tactile image. And now we have a neural network that basically gives us the contact image. This neural network is very general. We just train it once, we call it like a calibration step, and then we can apply it to many of the sensors that we have. So you just need to accept that this is working really well. I'm not going to go into the details today, but I'm happy to, well, I can happy to go anytime actually. But it's just that this is a neural network that all it does is, given its tactile image, it tells us where there is contact. And the beauty of that is that this is object independent. It doesn't matter which is the object that is making contact. All this neural network has to do is predict where there is contact. So we just did it once as a calibration step, and then we just can move on. But instead, we do use the object for this simulation. So in simulation, we do need to have access to this model. But again, this doesn't mean that we need real experience. All we need is access to the object model, and then we can do all these computations in simulation. And what is important is that for the problem of tactile localization, we have reduced it to simply doing or solving the question of, is this contact image coming from the real sensor similar to any of the contact images? And if we answer that question, we will find that yes, actually there are some images that we can simulate that are very similar to that one. And that's going to be for us a way to solve this problem. This is a matching problem where we can get which contact image in simulation is more similar to that one. And that's going to give us an estimation of what is the post, the contact post that could have generated this image. So let's look into how can we make this matching happen. The question that we're trying to answer is, if we have two images, two contact images, are they close or not? If you think about it intuitively, I think we would all say that, yeah, these two contact images, they look similar. They probably come from the same or similar contact poses. And instead, these two are not similar. But then how do we quantify that? In simulation, we actually have the poses that generated those images. So in simulation, it's kind of easy because then telling if two images are the same or not, it just means, are they close or not? But this is just something that we can do in simulation because only in simulation, we have access to the contact poses that generated those images. But if we do, then all we need to answer is, are those two poses close or not? And the way we do this actually is something that is very standard. So answering this question, we just use, this is the equation. But the main idea of how to tell if two poses are close or not is we have the object model. We convert it into a point cloud. And now we're just going to look at the points of this point cloud. I'm just going to mark 3 for visualization, but actually we're going to look at all of them. And now we're going to put this point cloud into the two positions that we want to compare. We want to compare the error between these two poses. We want to say if they are similar or not. So now all we have to do is compute the distances between each of the poses of the points of the point cloud. And if we do that and we take the average, that gives us a pose error that takes into account not just translation, but actually also orientation. So you can see it in here, we put the point cloud at 2 different poses. And now we just compute the distance between all the points of the point clouds. And if we take the average, now this just gives us a different pose error. So I hope this gives us a good intuition of how we can get this metric that actually encapsulates what is the distance between two poses and takes into account both translation and orientation. So now in simulation, we have a way to say whether two poses are similar, and also that means whether two images of contact are similar or not. But in the real case, for this image, we don't know what contact pose generated. That's actually the question. We're trying to do pose estimation. So instead, what we're going to do is we're going to learn this metric of whether two images are close or not, using the fact that in simulation, we can compute it. So basically, now we're going to learn how to say if two images are close or not. And for that, at train time, the first thing that we're going to do is simulate a lot of possible contact images. So you have a sample of them. Usually for our problems, we sample between 2,000 and 10,000. Again, this depends on the object size, and it depends also a bit on the type of problem that we are trying to solve. But in our case, again, between 2 and 10,000 is sufficient. And then we're going to generate a new contact pose that doesn't belong to that set. And what we're going to say is, okay, can I find the one in the set that is closest? And that's going to allow me to put labels into the then set. Basically, it's going to be 1 for the two images that are close and 0 for the rest. And now all we have to do is encode them through a ResNet. In this case, it's the architecture that we are using. And this is going to give us some encodings. And now finally, all we have to do is compare those encodings. And if we do that, we get the predicted likelihood. And now this is the true label. This is the likelihood. All we have to do is propagate the difference between these two labels. And that gives us a way to train this encoder. So this is how in simulation, now we are learning to say whether two of the images are close or not. Just by predicting this distribution that the higher the value, the higher the likelihood that this image is the most similar to this one. So now we are at test time. At test time, we have already computed all these encodings. So this we don't have to recompute because these all just come from simulation. All we need to do is get the contact image from the sensor, encode it. So now we just have this encoder. Now we just compare it, and this gives us again a predicted likelihood. So now, for instance, we can look at the maximum value and say, okay, this is our best match. This is the image that is more likely to have generated this one. And because this image comes from a contact pose, I'm actually telling this is the best pose that explains this contact image. So basically in practice, what this means is that now we are getting a pose distribution, where the set of poses that are more likely to explain the contact image that we are getting from the sensor. So I just want to show you some results so that we can see how precise or how well this works. If you look at this object, actually we get really good error. So in this case, we just get an error of 2.4 millimeters. This is the median error. And this is because this object actually has very discriminative contacts. So this is what we call unique contacts. For instance, this contact, there is no other place on the object that you will make contact and it will look the same as if you were to contact here. And there are many objects like that. So here, those are objects that have very discriminative contacts, unique contacts, and for them we can have very good precision. So just to visualize a bit more what it means, 2 millimeters, let's look at this object. In this case, 10 millimeters look like this for this object, and our error is just 2.5. And here I'm just showing you comparisons of different errors. So as you can see, for instance, 1.5 is very close, and this is more or less, we are fitting in the middle. This is our median error, more or less would be like this. Hopefully you can see the red and blue of two different poses with an error of 3, 2 different millimeter errors. And one thing that is interesting is this case. So this case has very high error. Actually, if you were to make contact here, you will get a contact that is non-unique. Basically, a contact in exactly this region, we wouldn't be able to say if it belongs to this orientation or the flip one for this object. So in these situations, contact alone is not going to be able to give us the estimate, the true answer, because this is non-unique. And it turns out that this problem of non-uniqueness, which tactile cannot resolve, for some objects is kind of everywhere. So if you think about this object, it has a lot of non-unique contacts. For instance, a contact anywhere in this region, all those contacts are going to look the same, even though they correspond to different poses of the object. And now if you look at the errors of our algorithm, they are really high. Only if we use a prior, then we can reuse them. So now imagine we have a vision prior. Then if the vision says, okay, we can only estimate things between 10 millimeter error, then we can reduce it a bit. But again, this is still a problem. And this problem just comes from the fact that tactile is local. So if you just look at single estimates, you cannot disambiguate the pose. And this is true actually for many real objects. So here you can see some of those objects that we just find them on master. And as you can see, it's hard to see, but basically they have very non-unique contacts, and just doing tactile localization is not sufficient. But if you use vision, especially for some objects, some prior, then you can do really well. But again, this is not a problem of the algorithm itself. This is just the fact that tactile is local. So what I want to argue now is that if I actually look at the distributions that we are getting are meaningful, and they can capture this non-uniqueness. So let's look a bit more into non-uniqueness for tactile. So if you imagine this object and you get these tactile images, then those could correspond from two options. This pose and this pose could both generate this tactile image. Now, if we get these other ones, then there are these poses and many more that can generate this. So our prediction of tactile localization should be able to give us a distribution that takes into account all these possible poses, that makes them all be likely. Here's another example. This is what we call the pencil. If you make a contact here, again, there are many poses, and our algorithm is capable to identify that. It basically tells us that all the regions that look green are likely to be the poses that have generated this contact. If we look at another example, like grasping here at the tip, our algorithm is capable to say, actually, there's only this region that I think is very likely to have generated this. So this is a good contact. If you make contact here, then our algorithm for perception is more confident that it knows which is the region that best explains this contact. There are other cases, for instance, in this object, like this is again a non-unique case because there are two regions that are likely. So this contact is very similar to this contact here. And our algorithm can actually find and predict these distributions. So now in this case, you have this bimodality. So if you were to make a contact here, you wouldn't be sure if it's there or here. And this is something that we can recover. Again, this is very important when we are talking about observability. Is this contact observable or not? And just another example, if you're just grasping at the tip, then again, our algorithm is very confident that you're just grasping at the tip. So this is information that in the biggest scheme of pick and placing and manipulability, you can use to find actions that help perception. I think that's something very important to understand. Tactile alone will suffer from locality. So you will need to reason about those probabilities. But if you do, then you can aim for actions that really help you shrink as much as possible the uncertainty in your localization. So this is how it works for tactile. This is the pipeline. It turns out that the same pipeline can be immediately used for other sensing modalities and especially for vision. So let me just show how the same pipeline applies for vision. Now for vision, we are getting these depth images. And now what we are doing is we're taking crops. Each crop corresponds to a grasp. So for instance, now we crop this image, and here you can see the crop that we are getting, and you can imagine that this is a grasp where the fingers of the object are these kind of vertical lines. So this is how we are getting possible grasp from the depth. And now in simulation, we have access to this object model from which we can compute contact poses. And again, from these contact poses, we can use rendering techniques to simulate possible graphs. And from those graphs, we actually, again, can visualize them as grasp on the object. So now basically we have the same problem where we have a grasp coming from the real image, and then all those graphs that come from the simulation. And all we have to do is solve the matching problem in the same way that we did before for tactile. This gives us a distribution that again corresponds to distribution over poses. So this is the way that we can solve, again, the pose estimation using vision, and also gives us distributions, which is really nice because now these distributions can be combined with the tactile distributions in a Bayesian framework to get us an updated estimate of the object pose. And I just want to say that for vision, we are not the first ones to provide this approach. It just turned out that the one that we developed for tactile just very immediately transferred into vision. But this is something that there is more groups that have explored, and it seems to work really, really well also for vision. So as a summary, what is the benefit of using this image matching and using encodings? Well, the first one is that it gives us a way to encapsulate whether two images are close or not, but in the pose metric. So the contact poses, if those two are close, then we are going to say that those two images are close. And this is something that now we can learn with encodings. The second thing is that now we can compute things fast because most of the computations are done offline. When we are at test time, all we have to do is encode the image and then just compare encodings. And this can be done really fast. Again, we have done this in the lab at a frequency of around 50 Hertz, which is really fast. So this allows closed loop event perception, where you just keep estimating the poses of your object and act according to that. Another thing is that it gives us probabilities that are meaningful and that again can help us go towards precision, because now we have these probabilities, we can reason better about our uncertainty, and this allows us to get better precision and aim for actions that are more meaningful. And finally, we can use it to combine vision and tactile, which is something very nice because then everything merged together very nicely and in a way that is very natural. So this is tactile localization, actually visual tactile localization. And this component we can use now into the big system of pick and placing. But this is not everything. So I have just shown you how to do pose estimation. Actually, if we now think about the big task of pick and placing, which we were talking at the beginning, it requires more things. And we can also learn them in simulation. Again, I'm not going to go into the details of how they work, but basically, beyond having visual and tactile localization, we also need to learn how to do this regress planning. So basically, if you have a set of possible grasp on an object, how do you combine them so that by the end, you can just go and place the object at the desired configuration? And we also had to develop a way to do task-aware selection, where we now are selecting grasp based on how good they are for stability. So is the grasp going to fall or is it going to work? Observability, is perception going to be able to localize the object? And finally, dexterity. Are we able to select a grasp that leads us to the minimum number of regrasp actions? So we had to do all those things in order for pick and place to work. And again, we did all of them just in simulation. So then given a new object in the real setting, we can just go and do pick and place operations. So now I'm just showing you how these are the real sensor images, and we can still solve all these tasks, but all these modules at the bottom, they just came from simulation. So now I'm just going to show you some results of how this works in practice. So now I'm going to show you pick and place for different objects. You can see them to the left of the videos. So this is the first one. This is an object that we have already seen at the beginning. And basically, now we are targeting grasps that are, again, observable, stable, and good dexterity. The next one is the pencil, the one that we've been talking about, where I mentioned that actually a good grasp is here at the bottom. So when we select grasp, our algorithm should be able to find those grasps that are going to be useful for perception, and actually can do that. If you look at now, it basically aims at this grasp at the edge so that it could just go, localize it properly, and then place it. Here we see another example. And here is just another, again, one of the bigger objects, but it's again able to just say, okay, if I grasp it at the edge, in this case, I get good localization. So it's capable to identify that and then just go and place it. So beyond cylindrical objects, we have also been looking at other ones. So here you can see this object. And basically when, again, we just give it to the system, and even from the first time, you can just go pick and place it with precision. Because again, our placements are pretty tight. And finally, here there are two more objects where we don't even need a regrasp. It turns out that in those cases, the pose where we're grasping the object is good enough for us to just go and place it. So again, there is a variety of strategies that the robot figures out on its own on how to go and place the object. And I think I've shown you some variety of objects, but our algorithm can handle even more variety. So I think the objects that you are seeing here on the screen are objects that we can do. And our goal is to keep trying to see and basically test the boundaries. What are the objects that we cannot handle? But I think all the ones that I'm showing in this screen, we should be able to use in our approach and be able to do precise pick and placing for them. So this is something that this project is still going on. And we definitely want to keep seeing to what extent we can generalize to new objects. And again, I think the ones that I'm showing we can handle. Okay, so a few more things. We can also allow different placing configurations. So just very briefly, here you can see the three objects laid in front of the robot. And then the robot needs to figure out at each time where is the best grasp to exert. And then it can just place them in different locations. So this is something that our system can just handle. And as you can see, it just goes and keeps picking each of them and then just placing it in different configurations. All of those are vertical, but we can also allow horizontal ones. So this is going to be an horizontal one where now the robot just needs to place the object here. And in this case, it can do that without even a regrasp. So it just goes immediately and just places the object into the desired configuration. Another thing that is important of this system is that I made the assumption right at the beginning, but it's very important that we have access to the object model. And the assumption was that, okay, this object model is a really good representation of the true object that we are using. But actually, we decided to challenge that. And instead, we said, okay, what if we use a reconstructed model to do all the offline computations? In simulation, what if we use a model that looks like this, that is clearly noisier compared to the object that we are going to be using in the real setting? And the way we reconstructed this model is just by using a rotationary platform and a camera looking at it. So a very simple method of reconstructing the object model. But now if we use it, and again, that means that we're going to use this reconstructed model in simulation. So perception, grasping, all those things are going to be using this simulated model that is a bit more noisy. Can we still apply it to the actual object? And it turns out that the answer is yes. So it seems that our system, to some extent, can also handle some noise uncertainty in the models that we are using for training in simulation. So now I want to recap on how I have shown you about precise pick and placing. So the main components that we are using, again, is probabilistic, tactile, and vision estimation. So basically, we are using the information of the sensors to generate pose distributions that can be used to inform the system on where is the object with respect to the robot. Moreover, we have done that using task-aware planning. So when we are going to select a grasp on the object, we're going to do so that the grasp is stable, but also so that it takes into account perception. So we are going to aim for observable grasp. And finally, we are also going to aim for dexterity. So can we make sure that the number of regrasps that are involved until we go into the placement is as minimal as possible? And with those components, the system now is capable to handle multiple objects, again, without requiring any real interaction from those objects. It's capable to do that with placements that are very precise, that are very tight. So we can really get good accuracy and also good performance. I haven't shown quantitative results, but basically for some of those objects, we can get 95% accuracy, so succeeding at the test. So definitely the system is capable to transfer the models from simulation into the real system without compromising on precision. And finally, again, we don't need to use real experience in order to perform those tasks. So I want to end with talking about some lessons that we learned and also some future directions. The first one is reactiveness. And if you look at it, the system is not reactive. It's not meant to be. We have actually designed the system so that in some sense it's open loop. Once we get the tactile information and we make a prediction over the over the object post, we actually then just commit to it and then compute a plan and execute it. And still we are able to get good precision, which is great. But in a more realistic setting, I think we need to accept that sometimes there's going to be disturbances. So adding reactiveness is going to be really important. So this is definitely something that we want to do. And here I'm just going to show the sensor in order to say our sensors are capable to give us estimates at a high frequency. And our perception models are also capable to run at high frequency. So I think there is room for us to add this reactiveness into the system. And I think that's going to boost even more the performance that we are getting. Another thing that we actually is worth discussing about is object-dependent versus object-independent models. The models that we have been training are tailored to the specific object model that we have. But someone could say, can we actually learn object-independent models? Can we do a perception in a way that maybe the model is the same, but now we can handle different objects? And I think to some extent, yes, but there is a question of precision, sorry. Do you compromise on precision if you try to have a model that is too general? And my take on that is that for some cases, we are not going to be able to go beyond object-dependent models. There are some objects that are very specific, so we need models for them. But I also think there are tasks, such as, again, screwing or simply maintaining stability. You're trying to place an object so that it doesn't fall, kind of stacking objects. I think there is something there that can be general and that we can exploit so that we don't have to build object-dependent models for such cases. So I think there's going to be a balance. And this is something that I really look forward to investigate in the future. And then also in this line of building models, there's also a question of you want to be precise, but do you need to really have a perfect model in order for you to be precise? So probably there is a trade-off between how much do I need to reconstruct the model such that then I can just go and perform the task at hand. So I want to look into this problem of active exploration, where we build object models at the same time that we build general perception models, and try to use information theory to say, okay, how much do I need to reconstruct? How much uncertainty can I handle in, for instance, the object model, while I can still achieve the task that I want? And then finally, again, I want to shift precise generalization. I want to be able to solve multiple tasks without compromising on precision. Pick and placing is a good example of that, but I think assembly is probably a nice next step towards that direction, where now we not only have to reason about where are we putting the objects, but also we need to reason about what forces are involved within these assemblies. So I really look forward to simulating forces and understand if there is any signature of those forces that we can really use to identify when an assembly is successful, when it's not, and to guide us towards the process of solving an assembly task. And I think this is very important even to my kind of the end goal, which would be assembling IKEA furnitures. So I want to set a path probably through assembly of small objects that give us more insights into how do we achieve this precise task without compromising on generalization, and actually the other way around, where we can just solve many more tasks while still maintaining the precision and accuracy that we need. So with that, I'm going to conclude here, and I'm happy to take any questions.
Thank you very much. All right, any questions?
I had a question. I love the idea of using neural network embeddings and relating those to sort of pose quality estimates or pose closeness kernel. But I'm struggling with the idea of using ResNet that has these convolutional elements, because if I'm understanding you correctly, you're using activations deep within the network, but before a classification layer as the embedding. And won't those learn to reject translations because they're not needed for object identity classification? So don't you have sort of a vulnerability to translations with that representation?
If I understand, well, thank you for the question. If I understand it correctly, you're talking about the fact that when we do classification with ResNet, there is a point where we actually do what it's called an average pooling. And if you do that average pooling, then you start forgetting about translation, and
yeah,
that is completely true. And I should have put ResNet asterisk because we remove the average pooling.
Oh, okay.
Completely.
Yeah. Okay.
Like the first time that we trained, it was like, this is good, but not great. And then we look at it, it's like, oh, come on, there is the average pooling. So we just remove it, and then everything worked really well.
Okay.
So I completely agree. You have to remove that. But once you do, then it's just like a standard neural network, just a backbone, and then it works well. But this is a very nice insight. It took us one iteration at least to figure that out.
So I have a question also related to the embedding learning part. So in order to assess these things like graph stability and also kind of the uniqueness of the imprint you're getting, you first need to kind of do all the learning of the network. And I was just wondering how fast is the training of the network for a single object? And when you showed these uncertainties, and overall it's kind of like a 60 post space, right? Can you say something about how finely you discretize that space or how you sample that?
Yes, I'm just gonna go there just to get a better, probably to give more intuition on that. Okay, sorry, I'm getting, oh my goodness, too many slides. Maybe that was not a good idea. Okay, there we are. So the first question was about the grid. So the poses that we need for that grid are actually not that many. Wait, Dieter, actually remember me the first question, because I think I forgot.
Yeah, just how long does it take for the network training for an object?
I'm just going to stay here. So training of the neural network is actually pretty fast. 15 epochs are enough. And they are enough because we usually just took the 15 epoch and then we move on. So it's really fast, but I would say 30 minutes. It's definitely depending on which computer you're using. I haven't computed exactly, but definitely if you wanted to say, oh, I want to compute the model while I immediately get a good model for perception, that could be something a bit tricky. But it turns out that sometimes we have just tried, okay, let's use a model from a different object. Mm-hmm. Let's try to see how that one does on this new object. So to what extent models from different objects can help into a new one. And this is not perfect, but it's surprisingly good. It definitely beats just doing something random. Mm-hmm. So I could imagine you just saying, oh, maybe this new object looks a bit similar to this other one. Let me start from that model and just tune it a bit. And this, I think, has a lot of potential. So this could be a way for you to reduce even more the training time. But definitely this doesn't need days at all because it's really fast. And I think it's really fast because we have just simplified so much the problem. Now, all the neural network, all it has to do is say, is it similar or not? And this is something that even us as humans can just very easily say. And we actually just compare to simple methods where instead of just trying to do this comparison, we just say, okay, the neural network now needs to do the regression problem. It just needs to predict the full pose. And that works much, much worse. Because from one of those images just saying X, Y, Z orientation, that is a much harder problem than actually just saying, oh, this looks similar to this other one. So this has been... And then in terms of the grids and the probabilities, the first thing to note is that those are contact poses. So this fact that there is a contact already moves everything into a 5-dimension manifold, because you're only looking at contact poses. So this already removes one of the distributions. And then the other thing is that here I'm just showing you one option, let's say, one of the possible phases, but actually there is the probability distribution is a bit larger. I just show you one of the options for you to see. And then in terms of our distributions, our grids, for this test, we say 1 millimeter. So we basically built a table, kind of a grid, And for each contact in this grid, there is at least another contact that is 1 millimeter close to it. This is kind of the resolution of these contacts. And if you do that for most of these objects, again, with 2 to 10,000 contacts, you have enough.
And 1 millimeter, and how do you do then the orientations? Is that?
Yeah, that's a very good question. So we basically discretize the orientation. So we use this notion of pose distance that I was talking before to more or less estimate how much a change in degrees in that orientation corresponds to 1 millimeter in that pose distribution.
Oh, okay.
More or less how we compute the orientation change that we need to include into our grid of contact poses.
Thank you.
Thanks for the questions.
Maybe I can ask one. When you're training your embeddings, like you're training with ADD loss. So, but you're asking, you know, if I have this pen, you want these embeddings to actually be the same to capture this like uncertainty because tactile is local. So, but it's not trained that way. So does it just kind of naturally happen? Or do you have to actually explicitly think about all the symmetries and invariances there are on the object?
Oh, that's a fantastic question. So the first thing is we use cross entropy. So we are definitely getting meaningful probabilities. So this is handled by the algorithm itself. So the things that we are producing are meaningful distributions. And then the second thing is, what about symmetries? We do handle symmetries, but the way we handle them is at the level of when we compute this kind of dense set of contacts. So when we compute this dense set of contacts, we say, okay, if this pose is symmetrically equivalent to another one, then we don't have to add it. And this is sufficient for us to handle symmetries because it's not the same a symmetry than a non-unique contact. Symmetries are easy to handle. As long as you know this is a symmetry, then you can incorporate that. And
yeah, I guess I'm thinking more about non-unique contacts, right? Because like all of these are non-unique contacts.
Yes.
So, but it seemed like during your training, you're asking all those embeddings to actually be different, right?
Yeah, they just emerge.
Okay.
So we are not detecting them during training at all. So these distributions, I was really happy the first time that I saw it because this is what it had to look like, and it actually looked like that. So the neural network itself, when it's just looking, we give the contact that is closest, but there could be another one that is also looking the same one. It just comes from a non-unique contact, a different pose. Well, the neural network, when it creates the embedding space, it already knows how to handle it. And as a result, we just get these distributions, but there is no, we don't specify. Usually what happens is like within the object has no non-unique contacts. So it's very discriminative. And then we look at the results and we realize, oh, actually these two contacts do look the same. So this has happened to us a lot of times. So it's just a neural network that figures out how to create embedding. And then it just on its own encapsulates this idea of non-uniqueness.
Great, thanks.
Nice question.
I have a question. I was wondering, like, how much does the goal configuration affect the grasp pose? And also thinking about regrasping, the ability to regrasp could also influence where you grasp the object. Is that something that you thought of?
Yes, that's a great question. And I don't go into the details of that, but the grasp that we perform on the object initially is influenced by how easily we are then going to be able to place it. So I think I showed some examples where we didn't require any regrasp. And this is because we aim at a grasp that will facilitate just going there and just placing it into the configuration. But now if I decide another placing configuration that is different orientation, then probably that grasp that we did initially is now not the best one. We need to look for another one. And the system its own can just figure that out. So we don't have to do anything as humans, right? The algorithm itself says, okay, this is my placing configuration. So now let me recompute what it means to be a good grasp for that placing configuration. And based on that, then it just selects the good grasp. So the placing configuration really affects even the initial grasp that we do on the object so that we can minimize the number of regrasps. So this is taken into account by the algorithm.
Thanks.
Thanks for the question.
All right, I think we are perfect on time. Thanks a lot, Maria, again, for giving such a great talk. Really, really exciting stuff. And thanks everybody for joining. and have a good winter break.
Thank you, Dieter. Thanks everyone for coming.
Bye.